Yes, thank you very much. So from Iwanaga-Gorenstein to Iwanaga-Gorenstein. Um, yeah, so thanks for the invitation. It's my first time to give a talk here at the Flash Talks. It's very nice. Um, so yes, I guess we are doing representation theory, and in representation theory, I mean the initial idea of representation theory is to not only study an algebra but also its representations, right? That's what representation theory is. So you want to study the module category of an algebra. And okay, sometimes this works very well, and sometimes, I mean, ideally, you would like to know all the modules. That's kind of a first goal, maybe then, and this is usually not achievable because we just know that many algebras we're interested in are actually wild algebras, and there's no hope to classify um, all all the representations. So then you might want to look at a certain subcategory, which is smaller and you can still understand. And this syzygy category, which I already know by CMP, obviously. I guess I will explain why CMP is standing for syzygy. Is a subcategory in this module category, this the category of all syzygies. And yeah, so we are the algebras we're interested in are typically of wild representation type, but can have finite syzygy categories. So this does not work. I mean, you can always study the category of syzygies, but not always will it be interesting. For example, if you have a hereditary algebra, then the category of all syzygies is just the category of the projectives. And so that's not so interesting. So you need some algebra where it is meaningful to do so, and these are these Iwanaga-Gorenstein algebras that we are looking at. So let me tell you what they are. So to be more precise, I not only require Iwanaga-Gorenstein, but actually I want of Gorenstein dimension at most one. And so what this whole sentence here means is that the projective dimension of every injective and the injective dimension of every projective is at most one. So it's a quite restrictive condition there if you look at it for the first time. But there's lots of interesting examples that come up, and I'll actually, you will see in part two. So this is part one of my talk. In part two, I will specialize to an interesting subclass. A syzygy is the same as a submodule of a projective module. That's what a syzygy is. And in this setting of Iwanaga-Gorenstein, the M is a syzygy if and only if it has no extensions with the algebra, which is if and only if it's a Cohen-Macauley module. If you don't know what this means, I mean, this is really the definition of Cohen-Macauley. Um, and so that's where this notation comes from. CMP, CM stands for Cohen-Macauley and P for projective. So the category of all syzygies that we are looking at is denoted by CMP. And then sometimes we will throw away the projective. So then we look at the stable category. That's when we underline. And so in parentheses, sometimes I have some comments here, which you may understand. If you don't understand, don't worry about this. If you do understand, well, even better. So this first is this Frobenius category, and the second is a triangulated category whose shift is the inverse syzygy. Okay, so good. So we have our first theorem, which says that the stable category of all syzygies is generated in the extensions by the radicals. So the rad A here is the radical of the algebra. This is a direct sum of the radicals of all projectives. So if you think about a projective representation of an algebra with a quiver, path algebra modulo some relations, then at every vertex of the algebra you have the projective, right? So you have your vertex here, and then you have all the paths that maybe they come together here. So this is the projective at I. And then the syzygy sorry, the radical is obtained by just removing the projective and keeping everything that's below. So this is definitely a submodule of a projective, so it is a syzygy, and so you have, for every vertex, you have one of those. And this theorem here says that the whole category is generated under extensions by all these radicals. And so generated under extensions means that it's the smallest category that's closed under extensions and also closed under taking direct summaries. Okay, so that's the general result. Now let me specialize a bit. And so we had Iwanaga-Gorenstein algebras, and now we do specialized to two-Calabi tilted algebras. These are the algebras we were interested in while we're coming from cluster algebras, categorifications of cluster algebras, and this is where these two-Calabi tilted algebras arise naturally. Examples of them are Jacobian algebras, so whenever you have a quiver with potential and defines Jacobian algebra, that's two-Calabi tilted. And special class of two-Calabi tilted is cluster tilted algebras, which are related to classical tilting theory. Yeah, so anyway, so let A be such a two-Calabi tilted algebra, and then I take a reduction of it. This algebra B is a quotient of A by some ideal J, and J is of this form A, the algebra A times an idempotent EI times A, where I is the idempotent at a vertex I of the quiver. So if the way to think about this is this algebra B is obtained from A by removing the vertex I. Okay, so the quiver, in particular, the quiver of B is the quiver of A, where you remove I and all the arrows adjacent to it, incident to it, and then you modify the ideal also accordingly. And then you can ask the question, well, does it happen that these two algebras have the same syzygy category? Note that you lose a projective when you remove a vertex, so they cannot be the same syzygy categories directly. So you have to really look at the stable versions here with the underlines. Okay, so 10 minutes is quite short. So here's an example of to illustrate, here's an algebra. Here I remove the vertex 5, and then you have some relations here, and then you have these relations come also with this construction by taking the quotient. And so you can ask, do they have the same syzygy category? And so let's go for our main result here in this setting. So theorem 2 realizes this syzygy category of the algebra where you remove the vertex inside the module category, or inside the syzygy category of the algebra A. So this J perp is a perpendicular subcategory. So it's the objects that have no extensions with J in either direction. And then you quotient by J itself. And you get the syzygy category of the algebra B. And so in particular, you get a couple of equivalent conditions when these two algebras have the same syzygy category. And instead of going through this, let me look at this example again. So here, the two algebras, you see the condition D here says that for every vertex J, so the projective at vertex I, the one that you remove here, I is 5, if the projective at J contains 5, then it must contain the whole P5 as a submodule. So you have to look at all these projectives. Okay, of course, P5 contains itself, but the only projective that contains 5 is P3, and it contains the whole P5 as a submodule. And so this condition D here is satisfied. So in particular, this condition A is satisfied. So they have the same syzygy category. So here's how they look. So these are very small syzygy categories. Here's the syzygy category of A with the projectives in place as well. But if you focus on the non-projective ones, then it looks like this. This is a two-cluster category of type A2. And the syzygy category of B, well, has the same shape. So if you really just look at the stable part here, these are equivalent categories. Note that the entries here are slightly different. There's a functor which describes this relation between the two. But yes, so the categories are the same if you don't think about the projectives. I'm already out of time, so let me thank you for your